run through them quickly. And then we're going to do chapter 14, and that is conjugated systems and the Diels-Alder reaction. In terms of the handout, compound number 1 was very simple. Molecular weight of 58, 3 carbons, 6 hydrogens. That's 1 degree of unsaturation. So we have a carbonyl, most likely we have an oxygen, could be an OH group, however, and a ring. We need something, ring, carbonyl, whatever, double bond. We have a molecular ion here at 58, and we have a base peak at 43. Now, whenever you see 43, you obviously think a psyllium ion or isopropyl. So that's about all we can say here. Could be an isopropyl, could be an acylium. Looking at the IR. IR is very classic. Starting down here, 3400, we have nothing to suggest an OH. We really have nothing here for sp squared CH. Got a nice sp cubed CH. No aldehyde peaks. Make sure you always look for those. 2700, typically 2 of them. No triple bonds, but a really big, nice carbonyl. Nothing here in the double bond region at 1600, so we're dealing with a simple aliphatic ketone. If we look at the NMR, proton NMR, we have 1 peak. That means that we have 6 identical hydrogens, so probably 2 methyl groups. C13 NMR, singlet up here at 206, that's a ketone, and a quartet, that's methyl groups. Put it all together, a psyllium ion, 2 methyl groups, carbonyl, this is simply acetone. Any questions? That was nice and simple. Compound 2, molecular weight about 160. When we talked about degrees of unsaturation, I forgot to mention halogens. When you have a halogen, you just pretend it's a hydrogen. So this has no DUs. Really a very simple sort of mass spec. We have a mass peak here, and then we've lost something, 29. I'm not quite sure what that is. Ethyl group weighs 29, so that's a decent guess. We have an iodine in here. What does iodine weigh? Well, it's like, 127. How about that? The IR, totally uneventful. Down here in the very low region, we have nothing to suggest OH. We have no sp squared. We have nice sp cubed. Nothing here for triple bonds. Nothing here for carbonyl. And nothing for double bonds. So we're dealing with a nice, simple, aliphatic iodide. Our NMR. Whenever you see a triplet and a quartet, in a ratio 3:2 especially, it screams at you that I am an ethyl group, right? I am an ethyl group. So this is an ethyl group. We have 5 hydrogens here, 5 there, they're all accounted for. C13, we have a quartet and a triplet. That's an ethyl group also. Very simple. Putting it together, we have an ethyl group and we have an iodine. This is simply ethyl iodide. Any questions? All right, C6H12. That's 1 degree of unsaturation, isn't it? No oxygen, so we're probably dealing with either a ring or a double bond. The mass spec, well, we have a molecular ion here at 84, and we have, we have down here a peak at 41 that happens to be an M minus 43. So we could be dealing with an isopropyl. There's no oxygen, so it's not a cilium. Isopropyl is probably our best guess. So far, we're just guessing on things. The IR. When you look at the IR here, we clearly have no OH. You have a really nice little sharp peak here that would suggest sp squared CH. Beautiful, huge peak for sp cubed CH. Nothing in the triple bond region. Nothing in the carbonyl region. And we have a really, really nice double bond peak at 1600. That's one of the nicest ones you'll ever see. It looks like it's kind of an aliphatic alkene. So we've got lots of saturated, and we have an alkene functionality. Now the NMR. Well, first of all, we have 9 hydrogens, so that's going to be 3 methyl groups that are all the same. They're all the same. That accounts for lots of our hydrogens here. We're only missing 3. We have the 3 hydrogens show up down here. Now, remember, benzene rings show up 7, 8. And 5 and 6 are where we get alkene hydrogens. So these are probably alkene hydrogens. Now they're split up a lot. We have what would be a CH2 and a CH with a lot of complex splitting. But nonetheless, they're all in the alkene region. I would guess that it's something like this. This is our CH2, this is our CH. Now the reason that these are split up so badly is alkenes, of course, don't have free rotation, do they? So they can be like cis-trans sort of thing. So one hydrogen here is going to be trans to the CH, one is going to be cis. They have different coupling constants. And so they wind up splitting it up into a bit of a mess. But this is a good guess as to what it might be. If we look at our C13, again we have quartet here. That's a CH3. That's this guy. And we have a singlet and a doublet. So those guys. A doublet and a triplet. I'm sorry, these guys. And we have a singlet around 45. That's a carbon with no hydrogens attached. That's important. Carbon with no hydrogens. So, isolated carbon, and again, alkene region. Putting this together, we've got 3 methyl groups that are the same, a carbon that's sitting there by itself, and we have a carbon-carbon double bond. I think there's only one way we can hook these together, and that makes this. This is probably the most complicated of the set. But it does have a beautiful carbon-carbon double bond, probably the best you'll ever see. All right, this guy, C7H14. That's 1 degree of unsaturation. We have an oxygen, so it could be a carbonyl. Again, could be a double bond, could be a ring. For our mass spec, we have our molecular ion, and we have an M-43. 43 shows up again down here. So again, this suggests either a cilium or isopropyl. one or the other. For our infrared, we have no OH here. We have no peak on the high side of 3000. This is close, but doesn't quite count. We have really nice peaks here for the saturated CH. We have nothing in the aldehyde region. We have nothing in the triple bond region, but we do have this beautiful carbonyl. Looks like we're talking about a ketone. Again, no double bond peak right here. Again, it looks like a simple aliphatic ketone. Now, we have this interesting NMR. This is a doublet and a septet. Again, just like an ethyl group, this screams at you, doesn't it? It says, I am an isopropyl group. That goes along with it by a spec here. I am an isopropyl. We have 6 carbons, that's 2 methyls. Here's our single CH. We have 14 total, so we have 2 of these. We have 2 isopropyls in our compound. If we look at the C13, here we have a singlet. That's a ketone carbonyl. And again, a doublet, that's a CH, and a quartet, that's a CH3. Putting these together, we have a simple aliphatic ketone, isopropyl groups, acylium, probably an isopropyl cation too. I think the only way you can put this all together is to make diisopropyl ketone. Any questions? All right, we have a nitrogen in this compound. So we're either going to deal with an amine or a nitrile. Those are the 2 things we immediately think about. We have an amine or we have a carbon-nitrogen triple bond. Let's see. Carbon-nitrogen triple bond. We have 6 degrees of unsaturation. Whenever you have more than 4, you always think benzene ring. But that still leaves 2 more. So we're dealing with lots of DUs here. From our mass spec, well, we have a nice molecular ion. That's our base peak. And we have this peak at 76, that's M-27. And shoot, I don't know what that is either. Okay, so if I was answering this question, I would say M-27, I don't know. And that would be a perfect answer. Our infrared, 3400, we have no NH peak. So we know this is not an amine. Down here, we have a weak peak here that looks like sp squared CH. On our high end of 3000, we really have nothing. First time we've seen that. No peak that looks like sp cubed CH at all. Right here, 2200. One of the very nicest nitrile peaks you will ever see. This is a very classic carbon-nitrogen triple bond stretch. Obviously nothing in the ketone region. And down here, 16 and 14, 1450, these guys, those, you kind of see those things with a benzene ring. And that goes along with our degrees of unsaturation. So this looks like we probably have an aryl nitrile. Our NMR, only peak we have is down here. This is the benzene region. It's kind of split up a little bit, but it's still just one peak. There's just one type of hydrogen, and these are all hydrogens attached to a benzene ring. So all 5 of these are attached to the benzene ring. That's a monosubstituted benzene. If we look at the C13 NMR, we see a singlet and 3 doublets. Again, that's signature for a monosub-benzene. And we have this one other peak at 112. It's a singlet. That's no hydrogens attached. That could be our nitrile carbon. Makes sense. Monosub-benzene, consistent with a nitrile carbon. Again, putting them together, a benzene ring, we have a nitrile, only one place to put it. Benzonitrile. And our last one. Molecular weight of 171, but we see our molecular ions here are 170 and 172. That's okay, because we also notice it has a bromine. Remember, bromine has 2 isotopes over here. Average molecular weight is 80, but it actually consists of a 79 and an 81 in equal proportions. So that's why these are about the same height. We have 4 degrees of unsaturation, again suggesting a benzene ring. Big hunk and peak here at 91, that's our tropylium ion. And that tells us we have a benzyl group in our compound. All right, the infrared. We have nothing here for an OH. We have nice little peak here for sp squared. Same thing for sp cubed. We have nothing in the triple bond region. No carbonyl. And these guys, again, kind of look like, and these especially, a benzene ring. It looks like we're dealing with a simple arene with a bromine in it. The NMR. We have 2 types of hydrogens. 5 of them are on a benzene ring, down here between 7 and 8. 2 of them are down here. Again, there are no hydrogens adjacent to them, so they're both singlets. So this is a monosub-benzene, and this is a simple CH2. C13, we see a singlet and 3 doublets. Once again, monosub-benzene. And we see a triplet. That's our CH2. Down here, it's next to something slightly electronegative. We know we have a benzyl group based on our tropylium ion. We are probably dealing here with, there's our benzyl group, there's our isolated CH2, we have the bromine. Only way to put it together is this. This is benzyl bromide. Any questions? Well, since we did this as a quiz, we will not have an integrated spectroscopy problem on your first exam. There will be spectroscopy questions, mostly multiple choice or how many peaks in the C13 NMR would you see here? That sort of stuff. You know, symmetry. But no actual integrated problem where you have to do all those. All right? Any questions? Well, we're good then. Let's go ahead and do chapter 14. Chapter 14, Conjugated Dienes and Cycloadditions. Now this goes back a bit to last semester. Well, we're going to talk about double bonds and overlapping pi systems and things like that. This is retinol, vitamin A. Retinol has a long, continuous, conjugated pi system. It starts here. It's made up of alternating double bonds all the way down to here. These are all conjugated. When they're conjugated, you have these sp squared centers, have a bond in between, sigma bond, another sp squared, sp squared, etc. This is a classic example of a conjugated system. Now we remember from last semester that a simple alkene, we have one sigma bond. It's an sp squared origin on each carbon. And the additional p orbitals are orthogonal to the plane here. And they look something like this. These p orbitals overlap, top and bottom. And this makes up the second bond for our carbon-carbon double bond. One is the sigma bond, and the other one is this pi bond. Again, these are overlapping p orbitals. Now, these overlap well enough that we really have very hindered rotation around the double bond. If we tried to rotate this as the orbitals went orthogonal, 90 degrees across, the overlap integral would drop to 0, and that's bad. So it doesn't happen. When we have a conjugated system, again, we have a sigma network, and each of these also have p orbitals. P orbitals look something like this. Again, a p orbital on every sp squared carbon. And as you see, you can get nice extended overlap from one end of the system to the other. Now, these are regular alkene bonds, and as such, the barrier to rotation is very high. Turns out that the sigma bond in between here, the sigma bond, does still have some barrier to rotation, but it can occur. So if you heat this guy up, you can actually spin around this bond. You have to put in some energy to do it, though. Any questions? All right, let's just review again some chemistry from last semester. How do you make these things? Simplest way, if we take an alkene that has allylic hydrogens. Now remember, an allylic hydrogen is simply a CH or CH2 that's adjacent to our double bond. These are very reactive with something like n-bromosuccinimide in carbotet, and we will form the allylic hydride. I'm sorry, the allylic halide, not hydride, halide. The mechanism here, NDS, we're going to generate bromine radicals. We're going to abstract the hydrogen here. And when we do, we're going to form this radical. This is a conjugated radical. It's conjugated, and we have radical character both here, where it used to be, and down here. Simply flip the electrons back and forth to make the conjugated system. This is why it works so well, because the radical you form is very, very stable. So we're going to make the allylic radical. Once we have that, again, radical character top and bottom, bromine can simply add to either carbon, actually. And when it does, you form the allylic halide. And then finally, to make our conjugated system, we simply do an E2 elimination with something like tert-butoxide and tert-butanol. Do the elimination here. The conjugated is the favored product because the conjugated system is nice low energy. Any questions? That's just review. Now we remember again from last semester that we can take an alkene and we can add something like HBr. We know that this follows Markovnikov's rule. Markovnikov's rule has hydrogens in it. We don't really think about it that way. We think about the fact that it's going to form a carbocation intermediate. So in a Markovnikov addition, we are going to add the proton in order to form the most stable carbocation. So, start off with a simple alkene here. This is the diene. We could do an addition to 2 of these carbons, and we could form this as our product. We put our proton here on carbon 1, form the carbocation here on carbon 2, and simply add Br- to that point. That is simple alkene chemistry. However, when you have a conjugated diene, you can also do a second type of addition, and this is called a 1,4 addition. Now this starts off the same way. We're going to add the proton to carbon 1, that's this guy. Then bromine, bromide, will add to this carbon down here to form a 1,4 addition product. Now the reason this happens is because when we protonate here at carbon 1 to form this carbocation, that's what we talked about, Br- could add here, we did that, but this is, again, conjugated. We can move these electrons over, and we have positive character down on carbon number 4. So what you're really dealing with here is a carbocation that has character on both carbon 2 and carbon 4, and Br- could add to either one. We have our 1,2 product, or we have our 1,4 product. Any questions? So here's we did our 1,4. This again is our simple 1,2. Now let's talk just a little bit about this process because it's kind of interesting, I think. I was a physical organic chemist for many years, and I think mechanisms and stuff are very interesting. When you do this type of addition, things that we note, if we do this at low temperature, so we take our diene, take HBr, low temperature, ice bath or something, we're going to form the 1,2 product. If, however, we take and reflux this a bit, instead of the 1,2 product, we're going to get the 1,4 product. So the 1,2 goes at low temperature, the 1,4 at higher temperature. Not only that, but if we start off with 1,2 at low temperature, so we do the reaction, and we wind up with a 1,2 addition product, and then just let it sit there. Just let it sit. Eventually, most of it will go to the 1,4. So that means this addition must be reversible. To make the 1,2 quickly, but over time, everything goes to 1,4. This is reversible, and that means that the 1,4 product must be more stable. Now, the way physical organic chemists talk about things like this is to use these types of diagrams. Here's our diene, and here's our reaction coordinate. This is our 1,4 addition product down here. This again is the activation energy from here to here. The higher this is, the slower the reaction. The lower this level, the more stable the product. Now we know that the 1,2 goes faster. Therefore, its activation energy must be less. But we know that the 1,4 is more stable. Therefore, this is a less stable product. And if you give it enough time, you'll make 1,2. It'll go backwards, back and forth, and every now and then, some of it gets enough of a boost, go up the bigger hill, and make the more stable 1,4. So the 1,2 forms faster, but the 1,4 is more stable. When we talk about these two, and you should remember these terms because you might see them again. The 1,2 addition product is called the kinetic product. That means it happens fast. And the 1,4 addition product happens slower, but it's more stable, and so it's called the thermodynamic product. Kinetic, fast, thermodynamic, stable. Any questions? Well, let's do some chemistry here. Take this diene and do a 1,2 addition of HBr. Now remember, this is going to be a simple Markovnikov addition, isn't it? We're going to add the proton so that we get the most stable carbocation in the molecule. The most stable carbocation is going to be here because that's a tertiary center. So we're going to add this way, add our proton here to get our carbocation at this point. That is the most stable carbocation. Now it's a resonance stabilized carbocation, and we do have cationic character here and here. However, we're only interested in the 1,2 addition in this problem. Therefore, this is carbon 2. The second step is just going to be the addition of bromide, and we will make this as our addition product. Any questions? All right, our next one, same compound. Let's do a 1,4 addition. In the 1,4 addition, we're going to do exactly the same first step, aren't we? We're going to add the proton so that we form the most stable carbocation. Once again, going to add here and form this carbocation. But because this is a 1,4 addition, now we have to be aware that this is going to be resonance stabilized, and we're going to have carbocation character here on 2 and 4. So to get our 1,4 product, all we have to do is add bromide down here to carbon 4 to this carbocation center, and our product should look like this. Remember, the first step is always the same. You're going to add the proton to get the most stable carbocation. All right, 1,2 addition on cyclohexadiene. First step, we're going to add a proton to one of the double bond carbons in order to form the most stable carbocation. Now, the most stable carbocation here is going to be this guy because it is adjacent to this double bond and it will be resonance stabilized. So we're adding our proton to this carbon to form this carbocation. Once we've done that, the second step in the reaction is very simple. We're just going to add Br- to the carbocation center, and our product will look like this. Our last one here, let's take cyclohexadiene and do the 1,4 addition. Remember, it's going to start off just the same way. It's going to add a proton to form the most stable carbocation. So let's add it, and it's going to look like this. But because we're doing 1,4, now we need to address the fact that this is going to be resonance stabilized. And so we're going to have positive character on this carbon and down here as well. So to get 1,2, we add it here. To get 1,4, we simply add to this carbon, and our product looks like this. There's the whole thing. All right, look at these two compounds. What can you tell me about them? Well, this one has a bromine sticking up, this has a bromine sticking down, but they're the same compound, aren't they? They're both 3-bromo cyclohexene. Doesn't always work out that way, but this time it did. Any questions? On your exam, you will have, some problems, I don't know how many, dealing with 1,2 and 1,4 additions to dienes. So make sure that you understand how you can delocalize the positive charge and add to either center. Any questions? All right, well, the real high point of this chapter is the 4+2 cycloaddition, also called the Diels-Alder reaction. Classic example of a Diels-Alder. Even though this is actually a very poor reaction, very difficult to do. But you take a diene. So that's a conjugated system with 2 double bonds. And you take an alkene that we're going to call a dienophile. Dienophile means diene-loving. So we'll see that there are dienophiles that are much better than ethene, but nonetheless, this works. You put these guys together, you heat it up, and you form cyclohexene. 4 plus 2, 4 carbons plus 2 carbons, 6-membered ring with a double bond. Now what's happening here is what's known as an electrocyclic reaction. It's totally concerted. There's no intermediate. You can imagine the diene here sitting actually above the alkene, and you initiate an electron flow. The electron flow looks like this. Move these electrons in to make a bond, these to make a bond, these up to make our double bond, and we get our cyclohexene. The bond that we made are shown here in red. We made this bond and this bond. These used to be the ends of our diene, and now our double bond is in the middle. Whenever you're looking at a cycloaddition like this and trying to go backwards or forwards, you want to be able to identify the carbons of the diene and the dienophile. Very simple rule of thumb. These are the carbons of our dienophile, right? What you do is you identify your 6-membered ring that you formed. You look for the double bond. The carbons of the dienophile are directly across the ring from the double bond. Simple way to look at a compound and work backwards. Any questions? Well, before we delve into this too much, let's just look at some very simple examples just so you see the kinds of things that we do here. Take a look at these guys and very quickly jot down the products for these 3 reactions. Well, we've just seen the first one, so that's a gimme. Simple way to look at this. Think about the ends of your diene. Remember, the ends of the diene are going to bond to our dienophile. So the bonds we're going to make are going to look like this. When we do that, we're going to make a new double bond. It's going to be here between the 2 old bonds, and it's going to be there. So we're going to have 1, 2, 3, 4, 5, 6 carbons in a ring, and this is our double bond. Once again, the bonds that we made, always think about those 2, are these guys. This is our dienophile, and this was our diene. All right, our next one. Our diene is cyclopentadiene, so it's in a ring. Nonetheless, the carbons that are going to react are going to be the carbons at the terminal ends of our diene. And they're going to add to the dienophyte like that. Now, the product of this reaction is going to be a 6-membered ring that includes these 4 carbons and these 2, and we're going to have these 2 as a bridgehead. There's going to be our double bond. This is going to be the cyclopentadiene part. These are our 5 carbons of the cyclopentadiene, and here's our new double bond. To that, we attached our dienophyte down here. Once again, if you look across the 6-membered ring, right across here, these are the carbons of our dienophyte, and those are the bonds that we just made. So this is a bicyclic compound. There's our 6-membered ring on the bottom and a 1-carbon bridgehead. Any questions? Do the last one. Once again, the terminal carbons on the diene will add to the dienophyte. So we're going to make bonds from here to here and here to here. We'll get a new double bond in between these 2 right here. This is just going to be a 6-membered ring with a double bond, isn't it? And we have the methyl ketone simply attached. And it looks like that. Our rule of thumb, once again, we look across the 6-membered ring, straight across. These are the carbons of our dienophyte, and these are the bonds that we just made. Any questions? Now, if you've been paying attention here, as we did these reactions, you'll note that I always drew the diene in this sort of configuration. This is referred to as the S-cis configuration. In order for a cycloaddition to occur, our original diene must be in the S-cis configuration. Now remember, we said we do have some freedom of rotation around here. It's hindered, but we can do it. And that's why all these reactions require heat. We have to warm it up in order for the things to happen, because we have to get to the higher energy S-cis form for the cycloaddition to occur. Any questions? All right, let's look at exactly how this thing happens. I think once you see how it happens, it makes it much simpler to realize exactly what's happening. I'm going to take a simple diene and a simple dienophyte, and we're going to do our reaction. Now, remember that these are all sp² carbons, aren't they? We remember sp² carbons have p orbitals, that stick up and down that form our pi system. So for our Diene here, we have p orbitals that look like this. Now I put my Diene file at the bottom here, underneath it, tucked under the front edge. Why did I do that? Well, this has p orbitals too, doesn't it? And these are going to look like that. Now, by George, these electrons are nicely lined up, top and bottom, aren't they? This is how you make your sigma bond. The electrons in these orbitals simply pair up, and they form 1, 2 bonds. It's a concerted transition state, so it all happens at once. But they simply pair up to form sigma bonds. Now when they do that, this is no longer a double bond, is it? Because we've used up all the p orbitals. But what's left over? These two. That's why these two now show up as our double bond. So we use all of these orbitals to make our sigma bonds. These are left over, and here is our double bond. Once again, these are the sigma bonds that we made by combining the electrons in these orbitals. That kind of makes sense, doesn't it? Any questions? Actually, let's back it all up and do it again. Here's our Diene. Here's our Diene file. We line it up so that the electrons here are all aligned. That means they can combine to form sigma bonds. It's a concerted reaction that both happen at once. We're left with these two p orbitals, sets of p orbitals here, and that's our new alkene. Kind of nice and simple and pretty, isn't it? All right, let's go a little deeper into the reaction here. We're going to look at the stereochemistry of this addition. So, my goodness, where did the stars come from? Oh, that's neat. So we have stars in the sky. We have a Diene file down here, and we have a Diene. Now, I have drawn my Diene file in a cis configuration. Both of these are nitriles. Electron withdrawing groups work really well for Diene files. What's going to happen here is the terminal carbons of the Diene are going to react with the 2 carbons of the alkene. We're going to form these bonds, and this is going to be our new double bond. Everyone happy with that? Here's our 2 new bonds. Here's our new double bond. Now, this is our alkene. The way this thing is drawn is a little difficult to realize it, but this is a 6-membered ring. And this is actually in a boat configuration. Now remember that from cyclohexanes. This is in a boat style configuration. In our boat, these 2 hydrogens are our bridgeheads, and they're bumping into each other. Now we can see this by taking this and rotating it around. Let's do that. I'm slowly going to bring this edge up, this edge down. And when I do, I wind up with a boat structure of sorts. And again, here's our 2 hydrogens. these guys bumping into each other, and they still are. Now, we know that in a cyclohexane, that a boat is a very unhappy configuration because we have all of this bumping in and stuff like that. We have eclipse things everywhere. It's not good. So what a cyclohexane does is it undergoes a ring flip. In the ring flip from a boat, we're going to take this carbon and simply move it down. As we do that, we get down here like this, and now this is more or less a chair conformation. Finally, whenever I draw a cyclohexane chair, I like to draw it with my axial bonds vertical because it's easier for me to see it that way. So I'm going to take this and just rotate the whole molecule a little bit this way so that my axial bonds are vertical, and I have something like this. Now, the whole point of this exercise was to look at what happened to the dienophile. Our dienophile started off with cis nitrile groups. Here we have the two carbons of our dienophile. One is axial, one is equatorial. Remember, I'm sure you do, if you have 1, 2 axial equatorial, that means they're on the same side of our ring plane, and they are regarded as cis. Now, in reality, this is what it looks like. Not a perfect chair, but nonetheless, these are still cis to each other. It's easier to see this way, but here I've corrected for the bond angles for the alkene. But once again, these are so clearly cis. The bottom line here, the stereochemistry of the dienophile is preserved. If we have a cis dienophile, we wind up with a 6-member ring with our groups cis. If we have a trans dienophile, we wind up with a 6-member ring with the groups trans. Well, bottom line, for the dienophile, the stereochemistry is preserved. Any questions? Well, let's just quickly look at some dienophiles. I mentioned that electron withdrawing groups were good. Electron donating groups are really bad. Ethene itself is a very poor one. But you put things like carbonyls, nitriles, there's an ester, there's an acid anhydride. Those are all very good dienophiles. And they react very nicely in a 4+2 cycloaddition. Now, we can't do a 4+2 cycloaddition without talking about benzene. How could you make benzene? Not through a 4+2, too many double bonds. But you could make benzene through a 2+2+2. Now, this is kind of cute, actually. If we take 3 molecules of acetylene and kind of get them in the right spot, we can take and move these electrons around, make 3 bonds, and presto, we have benzene. Benzene is actually a natural product. It forms deep down under the earth, and it probably forms through a cycloaddition reaction more or less like this. Any questions? All right, well, let's go ahead and just do some more cycloaddition reactions. Very quickly, just jot down the products for these guys. Now these are actually very simple. These are all going to give substituted cyclohexenes. I just want you to be able to jot these down quickly, put in the appropriate groups on the Diene file, and of course recognize which carbons are which in our adduct. Our first one, here we have butadiene and acrylonitrile. We are simply going to form the nitrile. These are the bonds that we made. Look across the ring. These are the carbons of our Diene file. Our next one, we have an ester. Again, butadiene. Going to make bonds here and here. And our product is simply going to be our cyclohexene with the ester as a substituent. Across the ring, these are the carbons of our Diene file. Our next guy here, we're using an aldehyde. Same sort of thing, 6-membered ring, aldehyde substituent, and these are the carbons of the Diene file. And then finally our methyl ketone. Again, we're going to make our bonds like this. 6-membered ring, double bond, methyl ketone. Any question? Now these, of course, are far too simple. You would never see anything like this on an exam. These might show up on the exam, though. See what you can do with these guys. Our first one here, we have cyclopentadiene. Remember, we're going to add the terminal carbons of the diene to the carbons of our Diene file. And our product should look like this. Again, it's a bicyclic thing. Now, when we talk about doing this, remember we're going to like pucker this ring, make it like this, and here's our bonds that we made, etc., etc. But what I want to point out on this particular reaction is the stereochemistry and this carbon. Okay, the stereochemistry and that carbon. This is what's referred to as an endoisomer. Here I've puckered my ring, make it easy to see. I go ahead and do my double bonds. These are the bonds that we made in our reaction. But once again, the stereochemistry here is referred to as endo. This is essentially the main product you will get. You'll never get the opposite one, which sticks up, and that's called the exo. So let's take a break from doing these other two, and let's think about the stereochemistry of this particular reaction. As an example here, let's use our nitriles, and again, cyclopentadiene. This is the endoisomer, and this is the exoisomer. The endoisomer is the one that is observed, not the exo. Now, why is that? Well, it has to do with the way the orbitals overlap as you go through our concerted transition state. When you think about endo, think about it in terms of into the cavity. So here's the cavity of our six-membered ring, right here. This is the space down here. These guys are sticking down into the cavity. Endoisomer, yes. Exo, no. Here's a nice example, I think. This is a good dienophile, isn't it? Electron withdrawing groups, aldehydes, etc. Here is our five-membered ring, our diene in the proper configuration to see. Now, we've seen this before. We know that we're going to take the terminal carbons here, these carbons, and we're going to overlap them and make our bonds. The way this actually happens, so here's our endoisomer. The way that this happens, and the reason it happens this way to get endo, can be explained by looking at the orbitals. Remember, we have 4 p orbitals here, and we have 2 p orbitals here. There's our 2 for our dienophile, and here are the 4 for our diene. Now we're going to make these bonds right here. So those are the ones we make, right? Take the electrons and those p orbitals and make a sigma bond. But in this example, these carbonyls also have electrons, don't they? And they're actually in p orbitals. And they look something like this. Now, we've taken the ends of our dienophile and we've tucked it underneath all of these orbitals. So they all get to interact with each other. This is a stable arrangement. The more overlap you have, the better you are. If we looked at the exoisomer, again, we have 4 here, we have 2 here. We're going to make our bonds right here. But what a waste. These guys out here are just dangling out in space. They're not interacting with anybody. So it simply has to do with the ability of the ends of our dienophile to interact with the orbitals on our diene. Now with something like the carbonyl group, it's really easy to see. That's why I used it. But it also works on systems that don't have a pi system at all. Again, there are electrons there. The electrons like to snuggle up with other electrons. So bottom line, we always get endo stereochemistry. All right, back to this guy. Go ahead and draw our product. What we're going to do here is take the ends of our diene. This is going to be our dienophile, isn't it? Just an alkene. So we're going to make these bonds in our reaction. We already have a 6-membered ring with a double bond in it here. And we're going to make another one. And it's going to look like that. Now I didn't show the stereochemistry here, but the ring junction here is a cis ring junction. So both hydrogens pointing up. That's because it's an endo-isomer. Our last one. Now this one takes a little bit of thought. A little bit of artistic skill. We're going to take our terminal carbons here, these two, and bond them to these two. So it's going to look like this. So our dienophile is going to be sitting on top of this ring, isn't it? Now how do we draw this? Again, it's a bicyclic system, and it's going to look like that. Let's look at this a little differently, okay? Make it easier. We know our terminal carbons here are going to line up with the alkene carbons here. We're going to make a bond here and here. When we do that, we wind up with our bicyclic system. This is what we started with, and here is our new double bond. Now, if I gave you this and asked you to work backwards, what is the dienophile? You would simply identify your double bond. The problem is we have 3 6-membered rings to deal with, don't we? So we could theoretically go across to these 2 carbons. Theoretically, that could work. Not very well, but it could. We could go across the ring to these 2 carbons. Again, that would be ethene. That's not very good. Or, this is a 6-membered ring here, too, isn't it? So we go across this ring and identify these 2 as our dienophile. So 3 possibilities, but really only one works out well. Any questions? All right, well, we did stereochemistry of the dienophile. Remember what we said is the stereochemistry is preserved. Cis gets cis, trans gets trans. Let's look at the stereochemistry of our diene. Now this is going to give us a simple substituted cyclohexene ring. The first diene, again this is the S-cis configuration. The first diene we're looking at, if we look at our double bond here, we do carbon-carbon, carbon-carbon, carbon-carbon. This is a cis double bond, isn't it? Over here, we're going this way, and this way, kind of a Z. That's a trans double bond. So this is a cis-trans diene. All right, I'm going to take this cis-trans diene and react it with this simple dienophile. All right, everybody with me? So let's go ahead and make our bonds. Again, we're going to make a 6-membered ring with a double bond. And it's going to be a boat, just like we saw earlier. At the top of our boat, we're going to have our methyl bumping heads with our hydrogen. So once we draw in our bonds, here's our new double bond. These guys are bumping heads. Now, what I did in the set of slides that we looked at is I simply took and rotated this so that we could see it better as a boat. So go ahead and draw this as a boat with these two at the top bumping into each other. It should look something like this. Here's our methyl and our hydrogen bumping into each other. Now I want to make this into a chair because I hate boats. To do that, I'm going to take this carbon, follow the blue arrow, just rotate it down. Now, when you do this operation, it's easiest, I think, just to think about the local stereochemistry so that you always get it right. If we look at this, hydrogen is above methyl, isn't it? So we're just going to rotate it down. In this structure, when we finally get there, hydrogen is going to be above methyl. That's not going to change. So let's rip this guy down. Hydrogen is above methyl. Now finally, we want to take this and rotate it so that our axial bonds are vertical, so I can see what's going on. And when I do, I get this. Again, hydrogen is above methyl, and here's the two methyls that we started with. Now, what's their stereochemistry? Well, the way we've drawn it, this is axial, this is axial. Opposite sides of our ring plane, they are trans. Opposite sides of the ring plane, they are trans. If they were both equatorial, they would also be trans. Our bottom line here, we have a cis-trans diene, and we get 1,4 trans stereochemistry. Cis-trans yields trans. Now let's do our other example here. Instead of a cis-trans diene, let's do a trans-trans diene. This bond goes zoop, zoop, zoop. That's trans. This one is zoop, zoop, zoop that way. It's also trans. So it's a trans-trans diene. Now, just like before, we're going to make our bonds. We're going to wind up with a 6-membered ring with these 2 hydrogens at our bridge ends. It's going to look like this. Here's our new double bond. Here's the bonds we just made. Now I'm going to grab this bottom edge and rotate it up, just like we did, so we can see the boat better. When we do this, hydrogen is above methyl, hydrogen is above methyl, and here's our boat. Just like last time, grab this carbon, pull it down to here, and we get this chair. Hydrogen above methyl, hydrogen above methyl. So we didn't screw it up. And finally, let's fix it so that our axial groups are truly vertical. And it looks like that. Here's our 2 methyls. One is axial, one is equatorial. That, by definition, is cis stereochemistry. Same side of the ring plane. And putting it in words, we had trans-trans dienes, and we got cis stereochemistry. So let's look at our two examples here and review what happened. In our first one, we had cis strands. Cis strands yielded 1,4 trans stereochemistry. In our second example, we had trans strands, and that yielded 1,4 cis stereochemistry. So the stereochemistry here is a little more complicated than it was with the dienophile. Remember, dienophile is always preserved, but there are only two cases to worry about here: the cis strands and the trans strands. Once again, cis strands yields 1,4 trans. Trans strands 1,4 cis. For our dienophile, cis was 1,2 cis, trans 1,2 trans. This is preserved. Trans trans gives cis, cis trans gives trans. Any questions? Well, how does this show up on an exam, huh? This is an actual exam question. Won't be on your exam, not exactly like this, but close counts. And it looks something like this. Simple diene, simple dienophile, and just to make it easy, I gave you a skeleton. Go ahead, take this and put in the methyl groups as appropriate. Well, which are the carbons of the dienophile? Very simple to identify. We find our double bond, we go straight across the ring to these two. Right? Our dienophile here was trans. So that means the stereochemistry is preserved. You simply need to put in 2 trans methyl groups. Now you could choose to put them both axial, but nobody likes that. So it'd be correct, but equatorial is always better. So we're going to get our trans addict here, and we'll draw it as diequatorial. One pointing up, one pointing down. That's trans. Question. Now, our Diene here. Our Diene was trans, right? We remember because it's trans, we're going to get cis stereochemistry. We're talking carbons 1 and 4 relative to each other, and they have to be cis. So to get them cis, one has to be axial and one has to be equatorial. Doesn't matter which, but you need one axial and one equatorial. And it would look something like that. Now, in reality, the stereochemistry here would be a mess because you would have a bunch of enantiomers and diastereomers and stuff to deal with. But that doesn't matter here. Right now, we're just concerned with the stereochemistry of our atom. Any question? Now, remember how we looked at our product, and we worked backwards to figure out what the diene was as a dienephile. Well, that's called a synthesis, isn't it? So let's do some of these problems backwards. Go ahead and draw the reactants that you need to make each of these compounds. What you need to do with each of them is identify the dienephile, and the remaining carbons are going to be carbons of your diene. So with our first one, we look across our ring. There are two possible dienephiles here, aren't there? We could go across the ring this way and have these two carbons, and that would make it ethene. That is theoretically possible. But remember, ethene is a very bad dienephile. To do a reaction with ethene, you use what's known as a bomb, literally. It's this huge stainless steel container that you put your flask in, and then you bolt the thing closed, and you heat this up to some ungodly temperature. You do it in what's called a bomb room. Bomb room has heavy reinforced walls and usually just a glass ceiling. So if it goes off, the explosion goes up and not out. Kind of neat. Fun thing to do. But we don't want to use ethene. We want to go around the ring this way and identify these two carbons as our dienephile. So the bonds that we made were those. The top two carbons are our dienephile. So we have a nitrile on one carbon, just hydrogens on the other, and it looks like that. Now our diene. All the rest of these carbons down here belong to the diene, didn't they? There are 6 of them, and they're in a ring. There had to be 2 double bonds, because it's a diene. And so it is cyclohexadiene. All right, do this next one. Find the carbons of the dienephile and the bonds that we made in the reaction. Look across our 6-membered ring to these 2. Bonds that we made are these right here. So our dienephile, we have 2 hydrogens at this end, we have the amide at the other, and it's simply acrylamide. Now what's our diene look like? Well, that's all the rest of the carbons. It's going to be 1, 2, 3, 4 carbons and an oxygen. Our double bonds used to be here and here, didn't they? Because this is in the middle, so this is where our double bonds were. So this is furan. 5-membered ring with an oxygen and 2 double bonds. Our next guy, look across the ring from our double bond. We find these guys. The bonds that we made are simply here and here. So this was our dienephile. Now look at the stereochemistry there. We have one nitrile group down, the other one pointing up. Are these cis or trans? Down and up, they're opposite sides of the ring plane. They are trans. Now because stereochemistry is preserved, this must be a trans dienephile. Now, the remaining carbons for our diene, it's 1, 2, 3, 4 of them. We had 2 double bonds in there. This is simply butadiene. Any questions? Isn't this fun? This is real organic chemistry. This is fun. You think these were fun? Look at these. Even though they're cute-looking molecules, the very same simple rules apply. All right, our first one, let's find our double bond. Let's look across our six-membered ring. These were the carbons of our dienophile, weren't they? Which means that these were the bonds that we made. Across the ring is the dienophile. Now, what does our dienophile look like? It has 1, 2, 3, 4, 5 carbons. We know that this used to be a double bond, didn't it? And this guy still is. So what is it? 5-membered ring with 2 double bonds. Looks like that. Cyclopentadiene. 5-membered ring with 2 double bonds. Now, our diene is the remaining carbons. The diene used to have 2 double bonds, right? How many carbons does it have? 1, 2, 3, 4, 5. 5-membered ring with 2 double bonds. So what is it? Another cyclopentadiene. Now this is kind of neat, isn't it? A nice dimerization reaction to give this product. This one's trivial. You can whip this one out in no time at all. Our rule, we look across the 6-membered ring opposite the double bond to find the carbons of the dienophile. The bonds that we made were these guys. So our dienophile had a double bond. These are both hydrogens, no R, and a methyl ketone. Well, the structure of the dienophile is simply that. And what was our diene? Well, you probably figured that one out. Those are the carbons of our diene. Once again, there are 1, 2, 3, 4, 5 carbons. There were 2 double bonds. That's why it's called a diene. And it is simply cyclopentadiene. Any questions? That one was nice and simple. This one has way too many oxygens, doesn't it? But let's do it anyway. Look across your 6-membered ring opposite the double bond to find the carbons of the diene. I'm sorry, the dienophile. Across to find the dienophile. These 2 were the carbons. These 2 were the bonds that we made. Now, our dienephile had 1, 2, 3, 4 carbons, an oxygen, and 2 of these guys are carbonyls. This used to be a double bond. You look at this is an acid anhydride, isn't it? Carbonyl, oxygen, carbonyl. But the double bond here, it simply looks like that. Do you know what this stuff is called? Malic anhydride. What did we use last week? 1 week ago? We did a Diels-Alder reaction using malic anhydride. That was our dienephile. All right, what's our diene here? These are the carbons, 4 carbons and an oxygen in a ring, 2 double bonds. Only one way to do it, and it looks like that. Any question? On your exam, you will get some of these types of problems where we're going to do synthesis. And we're going to get a mixture of stereochemistry problems. The synthesis problems, again, are fairly simple. Remember, the steps are to look across the ring, find the structure of your dienephile, look at what's left, that's your diene. Let's go ahead and do a few more stereochemistry problems. Again, in synthesis mode. At one time or another, all of these that we'll look at, this next 4 or 5, have all starred on exams. So, now this one's very simple, isn't it? We have a substituted cyclohexene. We look across our ring. There's a double bond. We look across to find the carbons of our dienephile. And those are them. Now the real thing that you have to do in this question is identify the stereochemistry here. The nitrile and the methyl group, are they cis or are they trans? Think back to chapter 4. See, somebody told you you had to know this back in chapter 4. These are both equatorial. If you just look at them, this one's kind of pointing up, this one's kind of pointing down. They are both, they are trans stereochemistry. So our dienephile here is simply trans. Our diene is the carbons that are left over. The carbons that are left over are simply these 4, 1, 2, 3, 4. No substituents. This is just going to be a butadiene. Any questions on it? You know, just to refresh yourself from chapter 4, the hydrogen here and the nitrile, they're cis, aren't they? This is pointing up, this is pointing up. If this hydrogen and this hydrogen, opposite sides, they are trans as well. So that's just a simple way to do it, just remember that. All right, here we have a flat guy with some wedgies. Now the wedgies make it even simpler. We look at this, they're both coming towards us. This obviously, they're on the same side. They're obviously going to be cis. So we'll draw the structure of our dienophile. Simply are two nitriles and a cis double bond. And what else is left over? Well, we have 1, 2, 3, 4 carbons, nothing on them, simply a butadiene. Any questions? Okay, let's take it up a notch. Step 1, identify the carbons of our dienophile. Look across the ring from the double bond. There's our double bond. We look across this way. These two are the carbons of the dienophile. Step 2, what's the stereochemistry of the dienophile? Well, they're both pointing up, aren't they? If they're both pointing up, they're on the same side. And how do we say same side in organic? We say cis. You could also say Susamen, but cis is easy. All right, so now we're dealing with our back carbons. We have 1, 2, 3, 4, and we have 2 methyl groups. We need to decide, are these methyl groups cis to each other or trans to each other? Well, this guy's pointing up, this guy's pointing down. That kind of sounds transish to me. Now, we need to remember our rule. We have 1, 4 trans. Where did that come from? Cis trans gave 1, 4 trans. Trans gave 1, 4 cis. Therefore, our dienophile, our diene must have been, because we have 1, 4 trans, it must have been trans cis. So go ahead and draw it in with trans and cis double bonds. Methyl groups are trans, therefore this is cis trans. All right, just a couple more. Here I tried to be cute, and I just rotated the ring a little bit so the double bond is in a foreign sort of position. So you have to think about it just a little bit. Remember, we want to find our double bond, look across the ring, and these are the carbons of our Diene file. Oops, don't look at that. We have one that's axial. We have one that's equatorial. What does that make them? They're both pointing up, same side. If they're both on the same side, it means they are cis. All right, so these two carbons are taken care of. We can forget about those. What are we left with? Well, 1, 2, 3, 4 carbons, right? But do we have to worry about stereochemistry here? No, we don't. Because if these 4 are the Diene, only one carbon was substituted. So it's a Diene with one methyl group on it. This is our Diene file. This guy's only had one methyl group. These are both hydrogens. And so this is it. That's their structure. Just a Diene with a methyl hanging on. Couple more and we're done. Again, we have wedges here. Makes it easy. Both nitrile groups are pointing up. We look across our ring to our nitriles. This is our Diene file. And because they're both pointing up, that's cis. Now, what's left over here are these carbons here. 1, 2, 3, 4. Again, we have a methyl group, don't we? So it's going to be a simple Diene with a methyl group on it. Draw the structure. Take the time, draw the structure. I want to make sure you get the methyl in the right spot. These were the terminal carbons of the Diene, right? This one and this one. It's not on those. It's on one of the middle ones. Not on these two. It's on the middle carbon. Therefore, it looks like that. And let's do one last one where we have two things to worry about. Once again, let's identify our Diene file by looking across the ring. These are the carbons of our Diene file. What is their stereochemistry? Are they cis or trans? Well, they're both pointed up, aren't they? So that's cis. So we have a simple alkene, a methyl, a nitrile, and cis stereochemistry. All right, let's look at what's left. We're dealing with 1, 2, 3, 4 carbons, and we have methyl groups on carbons 1 and 4 relative to each other. So we need to identify their stereochemistry too, right? This guy is pointing down, it's axial. This is also pointing down, it's equatorial. They're both pointing down, therefore they're cis. So what's our rule? What gives cis? You can look back, just slide. Does cis strands give cis or trans strands? Trans gives cis. So we have a trans diene, a cis diene. Any questions? And that is chapter 14. Now, what's coming up next? On Thursday, we're going to do a lab called the Diels-Alder reaction. Okay? So we're going to do that one. The following Tuesday, I don't know what we're doing. We're doing something. I don't know. Maybe another lab. I don't know. Another lab. Our next class, we're going to go over the